you want to go?
Yes. He's being a little.
Do you want to go?
What are we doing?
We're curling.
Yeah. Are we doing the same?
No, we're gonna be playing more as like one team versus another team.
He got it.
Or and slash we're gonna be doing probably more about like we're gonna try some draws versus takeouts and stuff like that. So
When does off-ice training begin?
it begins right now if you want it to begin. Yeah, that's right. Yeah.
What's the most important?
So this app
Probably
is
the balance.
Yeah.
and
Yeah.
it'll be releasing 30 minutes. Then like $30.
Okay.
This is $31.
Salary.
15 minutes. Let me go on my phone.
Okay, let's try this out. Take out your notes. Stop talking. Jonas, turn around.
Can we blow up some pumpkins?
Can we blow up some pumpkins? No.
Can we done? Come on, man.
What? What? Hey, what class are you in? No. What class are you in? What class are you in? No, what class are you in?
Yeah, I only know.
You're in Chem 30, right?
I'm gonna.
You're in Chem. You made the decision to be in Chem 30. Chem 30 is non-stop. We're not allowed to have fun. Boss it, take the smile off your face. Let's friggin' go, okay? No, we're not allowed to have fun
It's
ever.
curling,
Chem
baby.
30. Yeah, we can have fun at curling, not in school. Come on, here we go. What?
I said we should have done a lab.
No. We're gonna have a lab. We're gonna do a lab on Monday. Is that okay? And we're gonna go make some batteries. So, okay, sit down, be quiet, shut up. Here we go. Let's try this. We should be able to answer a list of like 7 things related to voltaic cells. So the first question that you should always be thinking about is what are the oxidation and reduction half reactions for a cell? And then because of that, you should be able to label which one is the anode and the cathode. And then because of that, you should be able to label the direction of the electricity, so where the electrons are going from and to. Also, because of the anode and cathode, you should be able to label the direction of the ion flow. Also, because of, anode and cathode, you should be able to label if something is gaining
Or
losing mass. And then finally, kind of the last question we like to think about is what will be the voltage produced by the cell, or the standard potential by the cell. So we're going to go through this. We've talked about all of these things with the exception of number 6. We haven't talked about how to get the voltage off of a cell yet. That's pretty simple, but we'll go over that here in a little bit. So draw the silver lead voltaic cell. So one side is silver. Hey, if you put silver metal in here, what solution should you put in there? Silver ions, right? So typically that's silver nitrate. And the reason why we use nitrate is because all nitrate compounds are high solubility. So silver nitrate is high solubility. It can dissolve in water really well. Lead 2 nitrate is high solubility. It'll dissolve really well. What's the problem? What's the problem if you were to take this electrode and that electrode and swap them, but not swap the solution? You would get, one of these cells would be a spontaneous reaction all by their own, right? And if you have one cell having a spontaneous reaction, then you're not forcing the electrons to go through the wire. Why do we want to force the electrons to go through this wire? What's the purpose of that?
So we can power.
You can power things. If I got rid of this voltmeter and I stuck a light bulb there, then we could power the light bulb. If I got rid of the voltmeter and I stuck a speaker there, then we could power the speaker, right? That's the whole purpose. That's the whole, yes, exactly. Okay, so
What?
that's the beat, right? No? Okay. Draw the following cell and write the reaction involved. That's what I want to do right now. Oh, also we should have said, because you have the oxidation and reduction half reactions, then you can get the net reaction. So this is what I want you to do right now. I want you to put in, on one side is going to be copper and copper ions, and one side is going to be silver and silver ions. I want you to draw that for me, please. If you weren't here yesterday, this is going to be mighty difficult. When you're done drawing the cell, I want you to think of the list of all the questions that I could ask you about this. Anybody need a data booklet? Okay, that's obviously a sufficient amount of time for us to at least label the electrodes and the electrolytes. Okay, so this is the bones of what you should have on paper, right? On one side. Okay, first of all, does it matter if the copper was on the left side or the right side? No, it doesn't matter. Okay, so you could have put the silver on here or the copper on here. It doesn't really matter. Does anybody know what substance typically goes in our salt bridge if we have a salt bridge? Usually it's sodium nitrate, yeah. And so we're gonna say, okay, sodium nitrate is in there. So it's a solution of sodium ions and nitrate ions. Okay, well, what are all the things I could ask you about this cell? What's the first thing I could ask you? What is it? Yeah, I could ask you which one is the cathode and which one is the anode. First, I probably want to label the half reactions though, okay? So out of all four of these things, what's a possible spontaneous reaction that I could get out of all four of these things?
G2 plus electrons equals Ag.
So this is my strongest oxidizing agent, right? That copper 2 plus ions. And, sorry, nope. Goodness gracious, the silver 2 plus is the strongest oxidizing agent. And believe it or not, that copper is the strongest reducing agent. Okay, no problem. So the way I do this, the way I always try to go about doing this in a very systematic way is, well, if this is the strongest reducing agent, then that's the thing that we're starting with. Would you agree? That's the thing that's actually reacting. So you have to start with copper solid. Now what could copper solid turn into?
Copper ion.
It would turn into copper ions. And it would give away 2 electrons when it did that. And then the silver on the other side, so the silver ions are going to gain an electron and turn into silver metal. Perfect. So we've done number 1. We've labeled the oxidation and reduction half reactions. We could get a net reaction from this. That would be super easy. Would you agree? What's the lowest common multiple? 2 electrons, right? 2 moles of electron. So when I add this up and 2 of those, I'm going to get a net reaction of 2Ag plus reacts with a copper solid to make 2Ag solid plus a copper 2 plus ion. That's all we did. We just said, okay, you need 2 of these for every 1 of those so we can get our net reaction. No problem, whatever. Now what I want to know is which one of these is the anode or the cathode? Joe, go ahead.
Silver, the cathode.
Silver what? Silver ions are not the cathode.
Metal.
It's always the solid chunk of conductive material, right? So either this solid thing here or that solid thing there. Those are your only options for cathode and anode, right? So this solid chunk of metal, this is going to be the cathode. Why is this the cathode? Yeah, because Gercoa, the cathode is always related to the strongest oxidizing agent, right? And so the cathode, what's the solid conductive piece of material in here? It's the silver plus, it's the silver solid. Okay, so that's the cathode. Then that means that this solid chunk of conductive material needs to be the anode. Perfect, no problem. Let's move on to the next one. Where are the electrons heading towards? First of all, what part of the cell do the electrons move through?
To the positive.
Yeah, they're going to move to the positive side, right? But where do they move through? Do they move through the salt bridge?
Both.
Do they move through the wire?
Electrons.
Yeah, the electrons.
The electrons go from both.
The electrons don't go through both.
The top of the wire.
They go through the wire, right? Electrons only ever go through the wire, okay? And we're going to see why that is here in a second. So the electrons are heading from the anode to the cathode, right? But here, I just want you to take a look at the half reactions. Which half reaction is gaining electrons? The Ag plus, right? So if this thing's gaining electrons, then the electrons must be heading towards this side. Does that make sense? So if the electrons are heading towards this side, what side must they be leaving? That side. Okay, all right. So the electrons are heading this way through the wire. Not through the salt bridge, but they're heading through the wire. Okay, so we've got the direction of the electron movement. What about the direction of ion flow? Now let's kind of split this up into 2 different thoughts. There's 2 types of ions in our solution. What are the 2 types of ions?
Positive and negative.
Positive ions and negative ions. What do we call positive ions?
Cations.
Okay, yep, and then negative ions or anions. So we've got cations and anions. And there, does it make sense that the cations, because they're positive and the anions are negative, does it make sense that they will feel a force in opposite directions? If the positives go one way, then that means the negatives have to go the other way, okay? So I'm going to draw a little bit more of a picture down here. You don't have to draw this, but I'm going to kind of balloon this up really big so that we can take a look at what's actually happening. So this is my chunk of silver, and then in here are silver ions. And in here is a solid chunk of copper, and in here are copper 2 plus ions. So we've got copper 2 plus, copper 2 plus, copper 2 plus, and they're connected by a wire, and they're also connected by a salt bridge. Now, I know that we're kind of just rehashing everything, I get that, but I want to be very specific about this. Let's look at the half reaction. When this cell is producing electricity, are we going to be making more positive ions on the silver side, or are we going to be using up positive ions?
Using up.
We're going to be using them up. So on this side, the silver ions, they combine with electrons, right? So the silver ions, I did that too fast, I guess, I don't know. Group, ungroup, boom, love it. So these silver ions over here, they're going to combine with electrons and they're going to turn into silver metal. Do you agree? And then this silver is going to combine with electrons, and then this silver is going to combine with electrons. Okay, okay, so what I want to know, oh man, this is quickly devolving really fast. What I want to know is, where do we have more positive ions? Do we have more positive ions over here, or do we have more positive ions over here? On the left-hand side. So what that means is that where are the positive ions going to be forced towards? Are they going to be forced towards the right side or the left side?
Right.
They're going to be forced towards the right side. Does that make sense? They're going to be repelled. No, but that's okay. So they're going to be repelled by these positive ions. So the cations are going to be repelled by those excess positive ions over there, and they're going to move towards the less positive side. Where are the negative ions going to go? They're inside the salt bridge, right? Where are they going to go? They're going to be attracted to the excess positive charge. Does that make sense? This is the reason why the positive ions travel through the salt bridge towards the cathode. So the cations head towards the cathode, the anions head towards the anode. Now, you will never have to explain that to me. I'm trying to explain why the cations head towards the cathode and why the anions head towards the anode all the time. All the time that will be the case. Okay? All you have to remember, cations head towards the cathode, anions head towards the anode. Boom, Bob's your uncle, we're good to go there. Are we okay with that? That was just, I'm just trying to explain to you why that is. Okay, which one of these electrodes is gaining mass? The silver. How do you know the silver is gaining mass? Because it's the cathode, but more importantly, let's look at the half reaction. It's gaining an electron, but it's making a solid, right? This solid material, right? I tried to kind of draw it on here. The ions are combining with electrons, and they're depositing themselves on the side of this electrode. So this electrode is going to get bigger and bigger and bigger and bigger. And what's happening to this electrode? It's going to get slimmer and slimmer and slimmer and slimmer. Does that make sense? Yes. Yeah, okay. It's really important you take a look at the half reactions when we're talking about that. And then voltage we'll talk about later. Is it fair for me to ask you any of these questions now?
Yes.
Yeah.
I swear if you
Not
still have
voltage.
a quiz, I'm probably gonna want
No, you're not gonna have a quiz. When's the last time I gave a
it. I
pop
don't know,
quiz?
they just said, so is it fair if I ask you these questions?
Yeah, okay, alright. So if I gave you a quiz like next Tuesday, could we do that? Alright, fine, okay, alright. What I want you to do, I made a mistake, I changed this for some reason, but this is supposed to be zinc solid. So I want you to tell me 2 reasons why. They're pretty straightforward, but I'll give you a minute to think about it. What are 2 reasons why this cell isn't going to work? Write it down. And he guessed posted like 2 or 3 episodes yeah. No.
It's a salt ridge. Are you serious?
No, this is, I wanted to change that to zinc. And now that that's zinc, now that's
There's water in carbohydrates, right?
correct.
13 reasons.
One of the many reasons why coffee car batteries are so heavy. As a proper car,
This is the only thing that's safe.
a proper car battery is like,
So, riddle me this.
It looks like a bell.
31 minutes of a golf
What would be your reaction?
Why?
there's a battery on this. It's the car battery. What's the strongest oxidizing agent on the table? Fluorine, okay? We can't have fluorine gas. That's
I have a
too
dog.
expensive. What's the next strongest oxidizing agent?
Josh F.
Boom.
He looks just like
Yeah.
I'm so tired.
Lead oxide. You have lead oxide and sulfuric acid
Have you seen
in your
it?
car batteries.
This is
And so those lead oxide batteries in there are super, like very acidic and very powerful. Okay. Somebody give me one reason why this isn't going to work. Max.
Whoever's made this
Yeah.
has been a complete goof.
Oh, they've made a critical
They've
miscalculation.
like a capital offense.
Yeah.
They've switched.
Hopefully they're not going to get killed for this. But, you know.
Hopefully, zinc and magnesium have been switched. What this means for our hopeless student is that one of the metal will react spontaneously with the solution that it's in.
Yes, one of these metals will react spontaneously with the
Means
solution that
it
it's in.
sucks as a circuit because it doesn't push electrons into a wall.
Absolutely. Where are the electrons going to leave? What substance do the electrons leave from?
That one.
The zinc solid. And where do they go to?
That one.
The silver ions. Are they forced through some sort of a path so that we can take advantage of the flowing of electrons? No. The electrons go straight from here to here. So you're going to get a spontaneous reaction, and one half of a cell can't have its own party, right? So that's a problem. Yeah.
I get the next reason.
Yeah.
Salt tube.
It's a bridge.
Yes. Yes, Madge, we are missing that salt tube. The salt tube that we need.
Salt
So we're missing the salt bridge. Perfect. So that salt bridge, we need that. Why? Because as soon as, let's say this was actually silver, right? As soon as you get ions, or sorry, electrons moving from one to the other, then you get a buildup of charge on both sides, and that prevents the flow of more of electrons, right? So the battery will work for a short time, and then it'll totally stop. Okay, any questions? All right, if you're one of the few people who tried to do that review booklet, like maybe a couple questions yesterday, I don't know, maybe there was only 2 people that tried it. you would have quickly found out that you had absolutely no idea what the second example in the first question was asking you. So most oxidizing agents have a partner metal in the table of reduction half reactions. I would like you to look at your table of half reactions right now. And I would like you to look for, I don't know, find silver ions.
Got it.
Okay? If you look on the other side, what's on the other side from silver ions? Silver metal. So what about copper? Copper ions. Solid copper, right? Iron ions. Yeah, should be solid iron, right? Now, there's lots of those half reactions that don't have a solid partner. For example, look at the acidified permanganate half reaction. That's not what I want. So when you look at the acidified permanganate half reaction, are there any solids in here at all? No, I don't see any solids in this half reaction at all. So what that means is we have to partner up. If we wanted to use acidified permanganate, as our strongest oxidizing agent, we would have to partner it up with something that could conduct electricity, but also something that wasn't reactive. Could we partner up permanganate and acid with gold?
No. Sure, actually.
Yeah.
Could we partner up? Could we have in our half cell, just like we did here, could we have acidified permanganate as our electrolyte, and could we have gold as our electrode?
Sure.
Would that work out? Would
Well,
that?
actually, no, because it moves it downhill.
That's a downhill reaction. So you have a spontaneous reaction in its own cup. Okay, what other metals could we choose? Could we, instead of gold, could we choose
No.
mercury?
No.
Maybe.
Jordy, could we put liquid mercury and acidified permanganate in the same cup?
Okay, well, that's confusing. So I'm just
Okay, all right.
No, you can't.
Yes.
Okay, so if we did that, we would get a spontaneous reaction in one side, and so we wouldn't be forcing the electrons to go through to the other side, right? That's a problem. Max?
In the lab, we use potassium permanganate. Can we use potassium?
Yeah, but in the lab you're adding one liquid to another, right?
Yeah.
Yeah, but here we have to separate the two half reactions. In the lab, in the titration, we had the the reduction half reaction and the oxidation half reaction in the same cup.
Yeah.
Okay? Here we want to separate them. We want to separate the oxidation and the reduction from each other.
But if you had like a potassium stick and potassium permanganate, would that work?
If you had a potassium stick,
Like
a solid chunk of potassium,
Yeah.
would that work? A solid chunk of potassium? Would a solid chunk of potassium work?
Is it? Wait. Oh no, it wouldn't.
That would be the worst possible combination, right? Well, second worst possible combination. Yeah. What? Yes. As soon as you put the potassium in the water, it would explode, right? Because potassium and water, they make a spontaneous reaction all by themselves, right?
Oh, yeah.
Shelby, were you gonna say something, or?
Yeah, is that like a general rule like for always? Like it's like a fixated rule that it can never be a spontaneous reaction?
Your half cell can never be a spontaneous reaction. Because, just give me a second, Jordy, sorry. Because when we have a spontaneous reaction, like we have here, silver ions are really high up on the left-hand side, zinc's really low down on the right-hand side. So are we forcing the electrons to go from one side through a wire to the other? No. Well, that defeats the purpose of a battery. That's the whole point of having a battery, right? Is you want to force electrons to travel through something so that you can use that energy to power something. Yeah, Jordy. Can you close the door? Is that okay?
Does that mean it has to be non-spontaneous?
You have to have some sort of a non-spontaneous reaction.
How to do like aluminum 3 ions and like nickel? 3 ions, 3 ions. 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 3
So nickel and aluminum 3 ions. If you wanted, yeah, that could be a potential half cell. You could have a solid nickel as your electrode, and you could have aluminum 3 ions. But what's the problem with that, Jordy? As soon as you get a reaction, what's the aluminum going to turn into? The aluminum ions.
Solid aluminum.
Solid aluminum. So you're going to start coating the nickel with aluminum metal. So you're going to start.
Play things with gold? No way.
Kind of.
So, how would they be working with car batteries if you got something that's so up on the list? Do they just like have this good metal that they're like, this won't do anything?
Okay, let's take a second, just because that's a really good question. Stay a second. Calm down. So car batteries. What's the strongest oxidizing agent in our list?
Fluoride.
Fluoride. But fluorine we can't use because it's so reactive. It would literally eat through the plastics that contain the battery together, that hold the battery together. So that's not possible. What's the next strongest oxidizing agent? Okay, so PbO2 plus sulfate plus acid gives us lead sulfate and water. So what I want to ask you, Max, is there a chunk of solid in here?
No.
Yes.
Oh, actually, yeah, there is.
Yeah, so you can use lead oxide as your electrode.
Oh,
Does that make sense?
that's why we're on permanganate. It doesn't have solid, right?
That's why we're on.
Okay.
So we still haven't solved the problem associated with what do you put permanganate with?
He can't.
You have to no. You're not going to be able to put it on lead sulfate. The reason why is because solid lead sulfate would partially dissolve in the water. Anyways, okay, let's think about this. Let's think about a substance that is pretty unreactive so far. Let's think about an element that you haven't really seen yet inside here.
Neon.
Nah, neon, but it's not solid, right?
Solid to argon.
Anything in the far right row, right? But none of those are solid.
Can you make them solid?
No, you can't.
Freeze them up.
You maybe can, but if it's like minus 130, whatever. Yeah. So, anyways, what I'm trying to get at. What about something really closely related to diamonds, Joe? What are diamonds made out of? Carbon.
Awesome.
So you can use carbon, like the lead in your pencil. You can use graphite. And you can use carbon because it's unreactive. Do you see solid carbon on here at all?
No.
I don't see solid carbon on here anywhere. Yeah, you could. You could use like nanoparticles and stuff like
What about a
that.
carbon
But
polymer?
what?
A carbon polymer?
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 Yeah. Let's just talk about carbon for right now. Okay. So when you pair up permanganate and acid with carbon, something that's not on this list. Carbon doesn't react, so it allows electrons to transfer through. It's conductive, like your pencil lead is conductive, but it doesn't react with any of these redox reactions.
It shocks you when you touch your skin to it because your skin's made of carbon.
To a pencil?
No, to like a car battery.
No, it's you when you if you were to touch. Please don't ever do this. But if you were to touch the negative lead of a car battery and then touch the positive lead of a car battery, it would shock you. Well, it would be very bad. I don't know if you would die. There are certainly certain circumstances where it would be very extremely dangerous. Okay, but if you did that, the reason why you get a shock is because electrons want to go from one side, one terminal of the battery to the other. Hey, which one of these is the positive terminal of this battery? The cathode is the positive terminal of this battery. Yeah, exactly. See? Rar. And then the anode. So electrons are going from the negative terminal to the positive terminal. If you put your hands on a battery that's powerful enough, electrons will flow through you into the other side.
What about if you do positive?
If you do positive, so if you just turn around, then it goes the other way.
Well, it might not.
No, it will. It will. Okay. All right. So let's actually answer this question, Jordy question. Lithium-ion batteries.
Isn't that like a thing? Like,
Yep. Totally lithium-ion
just
batteries.
like, that's no metal in it as lithium?
Yeah, the metal in it is lithium. And what can you not have inside of it?
Carbon.
Can't have any water.
Oh.
Can't have any water inside of lithium. What? Is there carbon in water?
H.
Oh no, H2O. I mean like, is there just like carbon bits?
If you put carbon bits in water, there will be carbon bits in
Like
water.
there's always dust in the air.
Yeah, but there's. We'll talk about that later. Okay, most oxidizing agents have a partner metal that serves as an example or as an electrode. Example: the silver ions can gain electrons to turn into silver metal. So the reason why you want to put silver metal in that half cell is not because it's reacting, but when you turn silver ions into silver metal, you probably want to coat that silver metal onto more silver metal. Because that's, you can just, if you put silver metal onto silver metal, then it's not that big of a deal of getting it off again, because it's just a solid chunk of silver metal. What about oxidizing agents like acidic permanganate? Do you see any metals? No. For these oxidizing agents, we will use an inert electrode. So I'm going to draw a picture. I would like you to draw that same picture. Do you have any amount of room down here at all? Okay, you should have a little bit of room. Scale it, yeah, it's all good. Oh, I should do it this way.
Are we doing 2 cups?
We have to shade it.
Yeah, you have to shade it in.
Molten launching
We
carbon
do
or
have
pour
Yeah, what's the story?
What's the story behind the toilet in the jack-o'-lantern?
Yeah.
My grade 9 connection students were like, "Oh, we should put a toilet in there," and I was like,
Okay.
"Yeah, all right." You can do whatever you want. Okay, so in here. So in here, if we have MnO4 minus ions, and if we have acidic ions, so hydrogen ions, this carbon solid, so this carbon solid can act as an electrode. Carbon is kind of considered a metalloid, and so it's got certain characteristics of metals and certain characteristics of nonmetals. It's brittle like nonmetals, but it can conduct electricity pretty well. And so when the electrons, when we connect this thing to something else, when the electrons go through here, they have a free path to go into the solution to combine with the permanganate now. The carbon never actually reacts. Your inert electrode like carbon, you should never see it inside the half reaction, okay? So this half reaction is going to look like MnO4 minus plus how many electrons? Or sorry, how many? 8 hydrogens and 5 electrons, good. 8 hydrogens plus 5 electrons, and we're going to get Mn2 plus and 4 waters. Now, we haven't attached it to anything, okay? Because we're just assuming that this other half cell exists, but I don't want to specifically put anything there, if that makes sense. Did you see our inert electrode anywhere in this reduction half reaction?
No.
No, and that's because it doesn't actually react. All it does is allows the electrons to transfer through it to get to the solution. Are we good? Yeah.
So theoretically, I put my finger
Yep.
in permanganate.
In acidified
And
permanganate.
I put a wire on my finger and
Yep.
I connected the wire to
Yep.
the right thing over here.
Yep.
My finger wouldn't get hurt.
Is your finger only made out of carbon?
I thought it was only made out of carbon.
It's not only made out of carbon. Have you taken any biology?
I passed Bio 30 with a 92.
Okay. The diploma might be testing the wrong thing. This thing. Okay. Okay. Your skin is made out of compounds that contain carbon, right?
Yeah.
But does that mean that the compounds that contain carbon are pure carbon? No, so they don't have the same properties as pure carbon, right? Like the fats and lipids that your skin is mostly made out of, right? The proteins, fats, and lipids, they will be destroyed by the acidified permanganate. Acidified permanganate is extremely dangerous for you to stick your hand in.
My finger will lose weight, but it'll also lose life.
Yeah! So, that would be a spontaneous reaction. Okay, what I want to ask you, the last thing, and then we're going to move on to something. Holy guacamole. That's why I don't like Halloween. Halloween makes people crazy. It just makes people crazy. So let's think about this. This reaction, because it's gaining electrons, what would it be, the cathode or the anode?
Cathode.
Because it's gaining electrons, it would be the cathode, right? Okay? Now, what does the cathode typically do? Does it gain mass or lose mass? Usually gains mass, but do you see us making any solids in here? Are we producing any solids? No. Are we using up any solids? No. All of these are aqueous, right? And then this is a liquid. So what's happening to the mass of this electrode? It's staying the same. Okay? More than anything, I need you to look at why did I put number 1 being the oxidation and reduction half reactions? Because from those half reactions, you can answer any question about an electrochemical cell. As long as you have the half reactions, you can do anything you want. Go ahead. What did I say you were going to have to do? Draw. Draw and draw and draw and draw and draw. Yeah. Yes.
Thank you very much.
When you come back, you got to draw.
Absolutely.
Okay. That's a hesitant.
This is like the one thing I understand.
Okay. Good. I'm cautiously optimistic.
Wait, what? It's 2 carbons? What's going to happen? Just electrons?
Tell you, all I know to do is,
What is going to happen?
Yeah, diamonds.
On one side you have carbon in a solution of iron 2 and an iron 3. And on the other side you have carbon in a solution of acidified dichromate, right? So figure out what your strongest oxidizing agent is.
Oh, no.
Figure out what your strongest reducing agent is.
Not you, it's a me thing. It's me.
No, but they have to be on different sides.
Try harder.
Yeah,
Wait, I'm gonna have to
She's like almost.
Yeah, I know.
The guy who's playing
Sam Jam.
Oh, from doesn't even sound like
Hey, I found it. No, this was a strong watch. Solid chunk, right? There's 2 different irons, right? You're gonna have to figure out which one's
Oh, I found it.
Yep. Okay. Connect it with the wire.
Oh, I have to do a wire.
Okay. Now, what I want to know is, what's the strongest oxidizing agent? Look for any of these.
Oh, hold on.
Alright, Walter, answered every question but two. But neither electrodes, right?
Good.
And then voltage we can't.
Yeah. Is that
Do I
okay?
have to write the net?
It would be good for us to write the net reaction. Okay.
There you go.
Oh, it's almost like.
Oh. Okay. Is anybody having any trouble answering any of these questions? Okay.
How would you answer question 2? Like the second checklist label items that have
How would you answer number 2? Label the anode and the cathode? Okay.
they're both the same, so would it just be
So one of them's going to be one, and one of them's going to be the other, and you have to tell me which one is which, right?
okay, so we
Yeah.
just
You just, yeah, that's it. Yeah.
Like the IC goes.
Yeah, I know, I like that one the best. Just saying.
Gotta try.
One person, yeah, it's crashing.
Okay.
I mean, I'm on it.
So let's burn through these questions kind of as fast as possible. What's the strongest oxidizing agent in here? The acidified CR2SM, the acidified dichromate, right? So this is our strongest oxidizing agent. And what's our strongest reducing agent? Iron 2+, right? So this is our strongest reducing agent. So we're gonna write the reactions of our strongest oxidizing and strongest reducing agents. So Fe2+, because it's a reducing agent, it's giving away electrons. And because acidified dichromate is the oxidizing agent, Cr2O7 plus, is it 14 hydrogens?
Yes.
And is it 8 electrons?
6.
6 electrons. Holy. And then 2 Cr3 pluses and 7 waters. Now, we could make the net reaction, but I'm not going to. What's the lowest common multiple between 1 and 6? 6. Good. Okay, so 6 of those plus all those. Now let's think about this. Label the cathode and the anode. I understand they're both the same substance. So where's the cathode? Is it the carbon on the right side or the carbon on the left side? It's the carbon on the right-hand side. This is the cathode. This is the anode. Now, which one of these, sorry, where's the electrons going in here?
So the electrons always go towards
Yep, but also, you don't have to memorize any of those silly rules like electrons go from A to C, because which side is gaining electrons? This side. So that means electrons are heading towards this side. They have to be. So the electrons are heading that way through the wire. So our anions, our negative ions are going to be heading this way. Our positive ions are going to be heading that way through the salt bridge. Joe, you got to go sit down there. And then which one's gaining mass and which one's losing mass? What? Neither. There's no gaining mass and there's no losing mass here. What? Are we? Why is there no gaining mass or no losing mass here? Because the carbon's not reacting anywhere. We're not making any more carbon solid, right? So there's no gaining mass and there's no losing mass. Perfect. Are we okay with that? Yeah. Okay. Standard cell potentials are fairly straightforward. We have 20 minutes.
I say we just call her, have a chill to
Fine.
Halloween.
Preston's beat.
Get in the spirit. Get in the spirit.
Get in the holiday spirit, huh? See, I hate holidays, so it makes me not want to get in the
It's a
spirit.
time to celebrate.
It's a time. Halloween is not a time to celebrate.
Okay, it's a time to dress up and go scare little kids.
Yeah. Okay. What are you dressed up as?
Nothing.
Yeah.
I'm
So.
really just gonna go buy like 3 boxes of candy.
Oh, okay.
Chill at my house.
Yeah, that's fine. The dessert.
Rejoice with what's enough.
I really want to.
I know you want to get in the spirit.
You know what? This is pretty straightforward. This is pretty easy, and I'm just going to give you guys some work to do after this. Let's take a look. Let's take a look at our table of half reactions. On the side, there's a bunch of voltages, and I just want to teach you how to do it, and then I'll teach you more about this later on tomorrow. So on the side, there's the table of half reactions. We've got the voltages of each one. Basically, all this means is this is the voltage difference. This is the electrical potential energy difference between this reaction and the reaction that we define to be 0. So if I stuck the hydrogen half cell with any of these reactions, it would produce whatever voltage you see here. Okay, that's the idea behind it. Now, in practice, what that means is you can predict the voltage of any battery by using the really simple equation. The standard electrical potential energy of the cell is going to be the electrical potential energy of the cathode minus the anode. Just think cathode minus anode. So if we took this, what half reaction do we have going on here? Zinc. And what half reaction do we have going on here? We have copper. So which one of these is the strongest oxidizing agent and which one of these is the strongest reducing agent?
Copper's not the strongest oxidant. Wait, hold on.
Yeah, this copper is the strongest.
Copper 2 ions, the strongest oxidizing.
Reducing would be the solid too.
Strongest reducing agent is here. Okay? So what I want to know is which one of these is the cathode and which one of these is the anode. What's the only word you have to remember?
Gercoa.
No. Gercoa. So which side is the anode and which side is the cathode? So this is, right, like this solid chunk of metal is the cathode, and this solid chunk of metal is the anode. And what did we say? The electrical potential energy of the cell is cathode minus anode. So what's this standard potential that you see in the diagram?
Plus 0.34.
0.34?
Yep.
You look at the chart.
Oh,
So let's look here,
It's below.
and let's look at the copper, and so it's positive 0.34.
And then you do minus.
So we go positive 0.34 minus, what's zinc? Negative
Negative
0.76. Negative 0.76.
Ooh, that'd be positive.
110.
So we're taking positive 0.34 volts minus negative 0.76 volts.
110.
Boom. That's it. That's the last thing.
That was easy.
That was easy, wasn't it?
Yeah.
So what's the hardest part about actually doing this?
The negative.
Figuring out what's
It's
the
watching your negatives. If any, I did teach some of you math and common. Okay, it's like any other math course. The negative signs always trip people up. Watch your negatives, please, and thank you.
Do you want to
Okay.
Be negative.
So what I'd like you to do is I'd like you to just answer, give the standard cell potential for the next two. That's all. And then we'll work on this more tomorrow. That's it. That's all I want you to do for the rest of the class.
So,
Predict the electrical